Hello, my name is Woo Lee, and I'm the graduate student of electrical engineering. And I'll talk about quantum algorithms for solving ordinary differential equations via classical integration method. After suggests two approaches, but I only talk about the first approach. First, I talk about the classical time integral method, and then I talk about digital quantum circuit time integration. First, I will introduce one of the numerical analysis methods, which is Runge-Kutta formulation. Let's consider following ODE and ODE d over dt ut equals f utT, and ut is a n-dimensional vector with the initial condition. Then ut plus delta t can be represented as ut plus delta t and sum of bi ki, where ki is as following. And A is a matrix and B, C are vectors. Is that A be a one by one matrix with single element 0, and B, C be a vector with a single element each element is 1 and 0, then the ODE became Euler method. So I'll introduce how can we do on the arithmetic on digital quantum computers. First, let's see the continuous version. Let's define a position operator x, and which gives its position as an eigenvalue, and its conjugate momentum operator p, and p can be written as f dagger x, where f is a Fourier transform, and it can be thought as a transformation from position space to the momentum space. And these two relations follows. Heisenberg equation of motion means the time derivative of position operator equals minus I over high h bar times commutator of position operator and Hamiltonian operator. And canonical commutation relation means commutator of position operator and momentum operator equals I h bar. By letting h bar equal 1 and p be the Hamiltonian, then the time derivative of position operator equals 1, and by applying Hamiltonian p for time c, the position shifts by c. Now let's consider a discrete version. In an n-cubic Hilbert space, suppose that the position state consists of 2 to be n distinct states, and quantum Fourier transform corresponds to Fourier transform, and this x operator corresponds to the position operator, and momentum operator can be represented as f dagger xf. Then following operator acts as shifting position by c in modular 2 to the n. And the time evolution of the position operator can be realized by rotate z gates by this process. Now I will introduce the circuit for the add operation. Consider a system H tensor H. Then the time evolution to those addition by A to the second register. This is because the eigenvalue for the first operator X is A, so it shifts the second position by A. And this can be represented with QFT and the time evolution of X tensor X. And it can be implemented by using O and N square gates. This is an addition circuit for two quantum registers with n equal to. And this can be implemented with two cubic QFTs and three controlled rotate gates. And subtraction can be implemented by an inverse of addition circuit. Now let's consider a system H tensor H and time evolution of X tensor P shifts third register by A times B in a modular 2 to the n. This is because the eigenvalue of X tensor X times X is A times B, so the third register is shifted by A times B. And this can be decoupled with QFT and the time evolution of X tensor X. So it can be implemented by O and cubic gates. The multiplication circuit for three quantum register with n equal to, and this can be implemented with two cubic QFTs and four controlled rotate gates. To use a numerical analysis method, we need fixed point representation. So let's take A represent 2 to the minus q times A, and to represent the negative values, let's use 2's complement. For fixed point values, we have to divide by 2 to the q after multiplication. And similarly as previous operators, the operator MQ can do multiplication with fixed point values. And dividing with 2 to the q can be by dropping to zero state and swapping. For example, this circuit implements dividing by 2 in 2's complement. A0 will drop out to zero state, and A0 becomes the previous A1, and A1 becomes the previous A2, and A2 becomes A3. Now, let's solve this ODE. E over dt U1t U2t equals U2t minus U1t, and the analytic solution of the ODE is as follows. By using Euler method, ut plus delta t has to be ut plus delta t times fut. So this F1 circuit adds ut to the first ancillary register, then multiply by delta t, and this F2 circuit adds minus u1 to the second ancillary register, and multiply by delta t, and those ancillary registers added to the u1 and u2 registers. Then the result became u1 t plus delta t and u2 t plus delta t. These graphs are the result of the simulation and the analytic solution. This is the next slide. One may think that this circuit is just a limit of the classical algorithm, but it has advantages. this circuit can be used as an oracle. So you can find initial conditions given a desired state at the final time with a quantum search algorithm. And quantum computers can serve as parallel accelerators of subroutines within classical algorithms. Thank you for listening.
They will be confused as the advantage of quantum.
I think other the F1 and F2 parts, they're error parts, so you can activate the calculator.
By how much factor?
There's the right.
I understand correctly that this is not this does give an exact solution. It gives a simulated result. So how is it better than classical 2D simulations?
And better as in efficiency, but actually I don't think it has big advantages.
You're comparing this with Euler method? Euler method. So does it use I mean, not in classical Euler method. That's not necessary.
Just multiply the slope and the time interval.
So it's not get.
Yeah. This is the solution for the time t, and output is the solution for time t plus delta. Fixed value, fixed point value, and two. Like this. Their definition.